Okay. Let me go ahead and share my screen. Can you guys see that okay? All right, cool.
Yes.
Sweet. Thank you. Okay. So this project, you guys are going to be building a linked list. It's another data structure, just like your ABS or your ABQ. So it's just another data structure you guys are going to be making. It follows similar ideas in the sense that you are going to be building something that other people are going to use, right? This isn't going to be something that um, you build and then you see like, oh, it's doing this and that. It's something that a tool that you're building for other people. Of course, your main is going to use the templated linked list, so you'll be able to see it doing stuff. But it's a data structure, right? It's a tool for other people to use, and these are pretty common. These linked lists, they have different applications out in industry and other places. So the biggest thing is it's a templated linked list. So this thing is going to be templated out just like your ABS and ABQ. You guys should be familiar with templates at this point. So applying a template to this link list shouldn't be that much of a challenge. So let's go over this memory stuff real quick. So he gives a little introduction to memory on his spec sheet, and it basically talks about how pointers can point to things, and how memory is in diagrams like this, and how each memory location has like an address associated with it, or it can rely kind of like on the heap over here. Um, that brings us to arrays. So the thing about arrays is that they are continuous memory. So it's going to be memory that is just all in one continuous location in your machine. And that's why we have the ability to index them, going 0, 1, 2, 3, 4, and so on. Because those chunks of memory are just right next to each other. Um, and then he goes over like ways that this will break if you go past the memory that is allocated for the array, and he kind of breaks down some problems that we have with arrays. So one of the biggest thing is, and you guys dealt with this in your ABS and ABQ last lab, is that when you need to initialize more memory for the array, you have to create an entire new array, either double the size or half the size, or whatever size it need be, and then you have to manually copy over all the new data, and then you have to delete the old array, right? And as I'm sure you guys are more than familiar with, this is kind of a heavy-handed process. It takes a lot of time for the machine to do this. It's just a lot of computation that has to be done to give us, to give us like this functionality, right? Uh, so the solution to this, because some smart people were like, okay, this is a little bit too much. This is too much computation for what we want. So they came up with a linked list. So the biggest thing about the linked list compared to the arrays is that it is non-continuous memory. So this memory is going to be located randomly throughout the heap. All of this will be done with new memory, so dynamic memory. With all this said, there are plenty of implementations of a linked list where you actually do use an array as a backing data structure for the linked list. That is totally possible. But for this implementation of your linked list, it's going to be done using pointers. It's going to be done using dynamic memory and pointers, and a lot of them. And it's going to be done using non-continuous memory, because by nature, using the heap in dynamic memory is going to be non-continuous. So that's when you get a diagram like this that we're looking at, where it has the first element, or nodes is what we're going to end up calling these. So it has the first node, and that actually references the second node, or points to that second node. And then the second node points to the third, and then the third to the fourth, and then the fourth ends at a pointing to a null pointer. The benefit we get from this, we'll actually go over in a second, but I just want to make sure that it's clear that these things aren't next to each other. So you're not going to be able to iterate over a linked list like you would an array. You can't just access the linked list at 0, and then the linked list at 1, and the linked list at 2, and expect it to give you the first, second, and third element. With that said, there is ways to build functionality on top of this, but that's for you to do. It's not going to come out of the box like that, right? And I think you end up doing something like that in one of the parts. Um, I guess any questions up till now before I continue? I know I haven't talked about too much, but anything, any questions? Okay, cool. So one of the ways to kind of conceptualize this linked list, because once you guys start developing it, you'll realize that it doesn't feel very concrete. It's very like out in the air because it's all dealing with pointers and dynamic memory. So I think either coming up with mental models as far as like diagrams or like metaphors in real life are really helpful, right? That's just something that's done with programming to make it feel a little bit more real to us as opposed to just like typing words on a computer, right? So one way to think of this linked list is a line, right? Um, so in this line, we just have the first person in line, and then it goes to the last person in line and has a bunch of people here. Um, the way that I picture this is that each person is going to point to another person, and they know that that other person like exists inside of this line, right? Um, the best way to think about this is literally just pointing with your arm, and it's just pointing directly to the person, let's say in front of you. So, or actually, for this example, let's say they're pointing behind you. We'll say this is the first of the list and this is the end. So this first person is pointing like physically with his hand to this person, and this person is doing the same, pointing their hand to this person. So if I were to go to this line and I said to the first person, like, you know, who are you pointing to? He could tell me. He's like, oh, I'm pointing to this guy right here, and then I can go access that guy that he's pointing to, and I can say, okay, who are you pointing to? Um, and then I can keep going and doing that until I get to the end of the list where I ask the last guy, who are you pointing to? And he's like, nobody, I'm pointing to null. I'm pointing to a null pointer. And I go, okay, this is my end of the list. Um, this is an example of a singly linked list where there's only one connection between each person, where the first person in line knows about the second person. But the second person, if I went to him and said, hey, who's behind you, he could tell me that because that's who he's pointing to. But then if I asked him who's in front of you, he won't be able to tell me because he's not pointing that direction. He doesn't know that person exists at all. The only person that he knows is in this line is the guy he's pointing to. Um, and then we fix that by making a doubly linked list, which is a little bit awkward to think about it in line. But if you were pointing to the person in front of you, and then with your other hand, you were pointing to the person behind you, that would be something like a doubly linked list, or less awkwardly standing like shoulder to shoulder and kind of like pointing your hands at each other, right? This way, if I went to somebody and said, hey, who's on your left, who's on your right, they would be able to tell me both ways. And similarly, both people on my right and left are also pointing to me. And that's what's considered a doubly linked list, because each node knows about two nodes now instead of one. And as you develop and write this linked list, you're going to realize that gives you a lot more functionality, because you can iterate over the array like both ways. And then when you do some insertion and deletion, it makes that functionality a lot easier to write. The difference between a singly linked list and a doubly linked list, like as far as implementation goes, is there's a lot less overhead when you write a singly linked list because you have a lot less to keep track of. But because you have less to keep track of, it means your linked list has less states known about it, which means that when you go to write functions, you have to do a little bit more like logic work to figure out, where is everybody, right? With a doubly linked list, there's more overhead, there's more that you have to pay attention to, there's more states that you have to keep track of. But with that, because you have all these known states, you kind of know the way your linked list is set up, and you can access different elements quicker or different nodes quicker, right? Um, One note about the nodes, I mentioned those a few times now. A lot of people, when first starting this project, their assumption is that a node is a keyword in C++, like node just comes with C++. Um, that, oh, excuse me. That's not the case. A node is something that you actually have to make. And I'll go over that in a little bit after I'm done kind of going through the spec. But that is something that you're going to have to make. It's going to be a nested struct inside of your linked list class. Um, so another thing that linked list gives us, besides this pointer functionality, which looking at it just seems like overcomplicated, we don't really know how this is helpful yet. So one thing that it helps with is the insertion and deletion, where basically each time that you add an element or take an element away, you don't have to resize the entire linked list. You don't have to make a new list, copy everything over, and iterate that way. You can just simply delete that node, and then close in the gaps as the linked list sees fit. So, for instance, this guy can actually leave just in the middle, and then we can connect these two people together if it was a doubling linked list. Similarly, if we were adding a new guy here, we can lock these guys together to point to each other, and then lock these guys to point to each other. And with arrays, this would be a little bit more challenging because we'd have to take them out and we'd have to shift all the elements over. And really, when I say challenging, I don't mean challenging to write, because arguably this is a lot harder to write. I mean challenging in the sense of like for the machine, like that's a lot of stuff for it to do, as opposed to create a new array, or excuse me, to create a new node, and then just move a couple pointers around to point to different places, right? That's way easier than doing a for loop that has to shift through every element and shift them all down. That's way more computation heavy than just making a new node and pointing some stuff to it. So but you know, making things easier for the computer typically ends up making things a little bit harder for you. But you know, you only have to write it once. So any questions on this or anything I've talked about? All right, cool. So I think we're ready for me to actually, well, we'll go over this and then I'll go over the code I've written to kind of start you guys out. And then I'll do some drawings because you guys know I love to draw. So basically you'll be using a nested class in this project. So you're going to have my class, which is going to end up being your linked list. And then you're going to have a nested class, which is going to be your node. And you'll see that it's a struct. I'm not sure if he's talked about structs or not. But the only difference, well, one of the only differences between a struct and C++ is that everything is defaulted to public as opposed to private. So these elements inside here are actually going to be public and not private. That's just how the structs operate. Structs come from C, if anybody's familiar with like C language. It doesn't provide any object-oriented principles, but it does provide structs as a way to contain data. It's more of like a container, and then C++ built off of that and kind of made classes. But they're cool to use. Really, I think in my experience, structs are used when like you either want something to just default to public, you don't really care about having any private variables, or you don't want to really view it as an entire class. You don't need like copy constructors. You don't need any constructors at all, really. You can write them if you want to, and they'll work fine. But it's more of like if you just want a little like a box of data is kind of how I picture it. Where classes typically have, you know, like functionality built around them. They actually have functions. They have constructors. They have destructors. All that good stuff. Again, you can totally give all that to a struct. It will totally let that happen. But I think if you don't need any of that, that's typically when we default to just making it a struct as opposed to a class. So hopefully that makes sense. And then I think he goes over that. He says no particular reason. It's just, remember, a struct is a class with the public access by default. But I think everything I said is kind of what I've seen out there, that you know, structs are basically just classes that you don't want to add a lot of functionality to. So, but with that said, if you wanted to make this like class node, that's totally reasonable. That's fine. Just make sure that you make sure these things are public. So, here he goes over it a little bit more. You have a linked list class, nested node class, and then there's going to be about 3 things in each. You can have more if you want to, but this is pretty much the bare minimum that you guys are going to need to deal with. So with that said, let's just kind of, how do I want to do this? Let's go ahead and put this to the side, and this to the side. So I have this kind of written out for you guys right now. This is pretty much what you're going to be looking at. So if we compare what he has on the right and what I have on the left, it's going to be templated out, right? Because this is a template and it needs to store a T data. And then it's going to be a linked list class. And then you're going to have a struct node that is a part of the class. Some of you guys may be familiar with like inheritance and stuff like that. This isn't what this is. This is just the linked list containing a struct node. So only the linked list like knows about this like keyword like struct node. It's just a piece of data that we're defining within the linked list. But this isn't what like inheritance is. That looks a little bit different in C++, and we'll go over that in a little bit, like later down the road, not today. So if we look at the three things that we need the data that we are storing inside the node. So that's what this T data is. Some people get to this project and assume that data needs to be a pointer because basically everything in this project is pointers. But that's not actually the case, and let's kind of figure out why that is. So if you have a data structure, the whole purpose of a data structure is to actually store the data you're containing. And if we made data a pointer, that would mean it's simply just pointing to a location where someone else is storing that data. But we don't need it to be a pointer. We actually need it to be cat's laying on my keyboard as per usual. We need data to actually be a stack variable that can actually like store something, right? So that's why the data isn't a pointer. As far as the next and previous node go, those are going to definitely need to be pointers because they are going to point to the nodes to the left and right of this node, right? And something that might be syntactically a little weird is the fact that we're defining a struct node, and then inside of the node, we're actually using the keyword node again. And that's totally fine. We're defining node, and then inside of the node, it points to other nodes. So hopefully that kind of makes sense. Outside of this struct node and inside the scope of the linked list itself, we're going to have a head pointer and a tail pointer. These are going to be two pieces of data that keep track of the beginning of your list and the end of your list. And then on line 13, we have the node count. This is going to keep track of how many nodes you have total in your linked list. This is pretty much the bare minimum you need. If you wanted to add like more state variables, feel free to do so. But these are the most common variables that you're going to need, and I think personally the easiest to work with. So let me go ahead and draw some stuff up and talk about kind of the different scopes of these of the linked list and the nodes themselves. Because oftentimes in labs and office hours, these are the initial questions that I get. And this is kind of some places that confusion ends up being. So let me go ahead and just draw. Thanks, Kat. I'm gonna go ahead and draw a box. So this blue box is going to represent our like linked list. Like this whole box is the linked list itself. And these red boxes are going to be our nodes. Okay. So one thing that hopefully makes sense to you guys, because it's hopefully clear, that your linked list is going to be constructed of nodes, right? The whole building block of your linked list is going to be nodes. So, linked lists contain nodes, but nodes don't contain a linked list. The other thing that's really important is each node contains its own piece of data. So the linked list by itself can't like just access like data. It has to ask a node for data. And by ask a node for data, all I mean is you have to go into a node to receive that data. So let's kind of give a blown up version of how I picture these nodes. And everybody's like mental model may be different. So what I'm doing here, you might totally disagree with on how it looks to you. And that's totally cool. You can come up with kind of how it looks for yourself. But generally, I think this is helpful to people. So I usually split this node into 3 different columns. And I kind of picture this as these 3 different pieces of data that we have here. If you, for some reason, wanted to add another piece of data, then it would have 4 columns or 5 or however you want to picture it. But usually I think of this as, let's get a different color. Usually picture this left one as the previous pointer. So this is a previous pointer that's going to point to the leftmost. And then I picture this as the next pointer that's going to point over here. And then I have the data kind of in the middle, because the data is not really like pointing to anything on the sides, right? The data is just storing something. So that's the data is what this node is actually containing. So the big thing about this linked list is there's a lot of like state stuff going on in the background. Putting the data, like actually the keyword like data into a node is arguably the easiest part of the project. It's really keeping track of like what your linked list is doing that's challenging. So each of these nodes in the linked list look like this. So this is again just a blown up version of these things. So each different node is going to contain a different piece of data. So if we wanted to add a new piece of data to this linked list, and we called like add tail, which basically is putting something at the end of our list, we basically create a new node, and then we'd go ahead and store data inside of that node. And then we'd go ahead and connect the previous pointer of that node to the end of the list here. And then we're going to go ahead and point this next one of the tail to a null pointer, so we know it's the end of our list. And then we'll go ahead and make this our tail, our new tail. So let's go ahead and just like hack up something that kind of looks like that real quick. Let me go ahead and move all this stuff. Actually, before I do that, any questions on this structure? Like why it looks like this or anything like that? Okay, cool. Let's go ahead and move this. Let's see. We'll just make this bigger. Come on, get out of my way. I think I'm trying to make Visual Studio bigger, but it's not being real helpful right now. Let me stop sharing real quick. I don't know if that's getting in the way. Okay, cool. That seemed to work, but I think I also lost all my drawings. So the whole purpose was to preserve those. So that is unfortunate. Okay. Let me go and draw those up super quick. So we had our like linked list, and then we had some boxes, and then pretend these are doubly linked. Actually, I can just go add another one in there. This one is a little bit sloppier than our other linked list we had. And then we have those, and then we had previous and next and data. Okay, cool. So yeah, let's go ahead and write something that would be like an add tail function, which you guys are going to have. So it'd be good to pay attention, I guess. So let's go ahead, and I don't know if I'll actually end up doing the whole thing because obviously it's something for you guys to do, but I can at least get it started. And I think it's helpful to kind of see how these things work. So you're going to basically get a piece of data passed in, and this is, I think it's a return void. My disclaimer here is if you write exactly what I'm writing here, it might not work. I'm just kind of going off of what I'm thinking right now. So don't just copy what I have and then complain when it doesn't work. This is basically just to show you some kind of the syntax for how to work with these nodes. So if we get a new piece of data that's added in, the first thing we're going to want to do is create a new node, right? So what add tail means is we want to basically add something to the end of this list right here. Currently, this is pointing to a null pointer. So we have that much set up. And I'm writing this under the assumption that we already have a list set up, right? So you guys are going to have to kind of think of the edge case where your add tail is the first function being called. And it's creating just a brand new node, right? So the assumption here is that a list already exists. I don't know how to spell. There we go. I think that's right. So we'll go ahead and make that new node that we need. That's going to be pretty common. So this is going to be a node pointer, and we can just call it new node. and this needs to point to some new memory on the heap, right? And that new memory is going to be a node type. So obviously it's a node pointer because it's pointing to something on the heap that is a node type. And then we can just name it kind of whatever we want. This name is only going to be in the scope of the add tail. So we don't really care what the name is, right? It's not going to be preserved throughout the system. So when we create that new node, one thing that we should have set up from previous function calls is that our tail is pointing right here. So our tail, like remember this tail variable on 12, should be pointing to the last element in our linked list, right? Or last node in our linked list, rather. So what we can do here is set tails next equal to that new node. So what this we'll kind of break this down a little bit. So tail is referencing this last node right here because that's where it should be pointing at this time. Next, again, is accessing it's going into this struct right here, and it's accessing this next pointer, which goes to the right, which is the one that is currently pointing to a null pointer. So instead of it pointing to a null pointer, we've created this new node right out in memory, and it's got all of its different attributes associated with it. And now we're saying the tails next is going to equal the new pointer, which means it's no longer going to be pointing to a null pointer, because remember, next is a pointer type, right? So it points to something. So now it's going to end up pointing to, oh, that is terrible. It is now attemptively going to point to that new node. So that's kind of what this line is doing right here, because again, next is a pointer type. So this is a doubly linked list. So we also need to have the new node we just made. We need his previous pointer, which is over here. We need it to point back to tail so that it's actually connected, right? So we need to kind of go do something like this, where his previous pointer is pointing back to tail. To do that, we need to do new nodes, his previous, right? His previous pointer is going to be equal to tail. So basically, these two lines are going to kind of hook these two things together. They're going to point to each other. So now that we have that set up, this new node we have is essentially now attached to our linked list. That's how it actually gets onto our linked list. If we didn't do anything like this, that node would just be floating in space. And once we exited out of this function, we'd end up with a memory leak, right? So the other thing in the beginning that we needed to do is actually store the data inside of this. So that's just going to be the new node data. So we access the data that's inside the node, and we're just going to simply set that equal to the data that's being passed in. So that's what that would look like. The last thing we need to do is we are responsible. Well, one of the last things we need to do, we're responsible of keeping track of the state of our linked list. So if we just closed out of this function right now, let's just say we're done writing this function. One thing that would happen is if we went to add tail again, we've left our tail variable pointing to something that's not truly the last element in or last node in our linked list, right? So if we went through these steps again, we'd go ahead and end up making a new node again in space. And then we'd end up connecting these two together, essentially breaking this connection. And then we'd basically just be replacing the last element like every time, right? So hopefully that the problem makes sense. So to fix that, we just simply need to move that tail pointer to the last node in our linked list, which is just going to be tail is going to be equal to new node, right? Tail is simply a pointer. So we're just saying, hey, it's no longer pointing to where I was pointing before, and it's now going to point to the last element of the array. And again, I'm doing the tail in blue because I want to make it clear that it's in the scope of the linked list. Tail is in the scope of the linked list. It doesn't belong to nodes. Sometimes, because this can be pretty overwhelming, students forget like what belongs to which, so they'll end up being like, oh, their new node like tail equals like new node next or something like that. And like tail doesn't belong to any node, right? Tail is part of the linked list itself. And that might seem super obvious now, but once you get to writing it, it can start to be pretty confusing. So I know that when I first had to work on linked list, I was pretty lost on what was happening. I didn't have a firm grasp on it at all. Any questions about this? One last thing is we'll need to set the, you can do this at the end where you set your new tails next equal to a null pointer. Or you can either set your new nodes next equal to a null pointer. Basically, right now, these are doing the same thing because tail is referencing this last one. And at this point, and up here, new node is that one, and you can make it a null pointer before you even put it onto the list, which I probably recommend this. If you mess up where you write this line, like if we wrote this here, you basically be overwriting the connection we just made, and tails next would be equal to a null pointer here. So this connection would be broken, and then we'd move the tail over. So that's errors like that are what I see a lot. This whole project is like, you got to be very analytical on like what each line is actually doing, because one line doing the wrong thing is going to make the whole thing bust pretty hard. So any questions? So again, this would be the case if the list already exists. You'd have to do something different if it was the first node in the list ever. It's easier than this because you don't have any data to mess around with, but you have to set up your initial like head and tail states basically when it's the first element in the list. So cool. Okay, so it seems like you guys are okay with what's going on. So let's go ahead and just look back at the spec. Let's see, we can probably nuke all this. So the rest of this is basically him just going over the different functions you guys will write. So I'll touch on those a little bit. And then this chart basically just gives the benefits and drawbacks of the linked list and arrays, and kind of compares the two. So basically in this code structure, you're going to have print forward, print reverse. So this is basically printing the list from the left to the right, and then print reverse is going to be printing it from the right to the left, basically beginning to end and end beginning, right? And then you're going to make that same functionality, except you're going to make it recursive. And then you have some accessors, which are going to be returning the node count. I guess that's one thing that we forgot to do here on this add tail is you'll want to increase your node count, right? You'll want to increase that as well. So. And then find all. So I think, and don't quote me on this, I think he's giving you a vector of node pointers and then a value, and you're supposed to find all of the nodes that have that value, something like that. And then this find is basically just giving you data, and you return the node that that has that data. This find is the same thing, except this one is a const version of that function. And you'll see all of these down here is you have const versions of the get node, and then the head, and then the tail. So again, get node is just going to return the node of the index that's being passed in. So with the index, you can basically just count over your list with your indices. And then head, you're going to return the head node, and then this you're going to return the tail node. Let me touch on iteration real quick, because that's something I see come up a lot. Let's say, for instance, we weren't keeping track of a tail variable. You definitely should be. That's the easiest way to do this. But let's say, for instance, we don't actually have a tail variable and we just have a head variable. How would we get to the end of our list, right? Well, I think the easiest thing is going to be a while loop where you basically say while, well, first you need a node current pointer, and it's basically going to be basically it's going to be a pointer that's just going to start at the top of your list where head is, and then you're just going to move that current pointer all the way down your list. And you can do that while the current pointer is not equal to a null pointer. Because if you try to do this while it's a null pointer, you're just going to get a seg fault because you're going to try to go past memory. Like that pointer is pointing to a null pointer, and you can't check what we're about to do, where you set current pointer equal to current pointer next. So current pointer equals current pointer next is basically, if we go ahead and draw this out, this is basically going to be what your iteration is going to look like through pretty much the entire project. So if head was pointing here, we'll do that in blue just to stay consistent. If head was pointing here, then you have this new, just this class, this function variable called current pointer, which is going to point to head, which is basically pointing to the same node. And then you check if it's a null pointer. It's not, right? We know this node exists. And then we say current pointer equals current pointer next. So this is the current pointer, and current pointer next is this guy right here. So then current pointer is going to move to point to right here. And then it's going to go through this while loop again, check if it's a null pointer. It's not. And then it's going to go current pointer equals current pointer next, which is going to be right here. And then in this one, we actually want to just end on this last one. If we were to iterate this one more time, it would basically say, is our current pointer equal to a null pointer? And it's not. And we'd actually iterate a little bit past where we want to go, because this is a null pointer, and we'd iterate to point to a null pointer, which would be okay. That in and of itself wouldn't break the system. But if we wanted to get to our tail, now we're like one past where our tail is, right? So in reality, you just want to go till your current pointer next is not a null pointer. So then when we get to this location, we'd say, hey, is our current pointer next equal to a null pointer? And we see that it is. And then we'll break out of this while loop, and our current pointer will be pointing to this last index. And again, like I said, if we were doing that for if we were doing that in replace of us having a tail function, or excuse me, a tail variable, then instead of using like tail here, we would basically just use our current pointer, right? Because that's where it's pointing instead of the tail. So hopefully that makes sense. Any questions on like iteration? Because you guys are going to be iterating a lot for this project. All right, cool. Let's see here. Okay. So insertion. So you're going to do add head, add tail. Add tail is kind of what I just went over. About half the functionality. And then you have add nodes head, add nodes tail, where he's going to give you an array, and you have to add that entire array to your linked list. Your array isn't going to be the type the linked list is storing. You have to iterate over that array and add each element in the array as a new node into your linked list. And then insert after, insert before, and insert at are all different variations of you adding it, like probably in between nodes. It's possible that your insert like after, before, at could be like at the end or the beginning. That's totally possible, but those are usually used for if it's somewhere in the middle. And if you kind of think of what like insert after, insert before, and insert at are, is I think you can get away. I guess he passes in a node here. I think you might be able to get away with using like insert at in either before, after, or something like that, because just the way like the indexes like match up. So with the note on indexes, your linked list again isn't going to come out of the box with any type of like index functionality, right? So you're basically going to have to count your indexes, or your indices rather, when you actually loop through. Meaning like in this while loop, if they told you to go to like index 4, you'd have to wait until in this loop your count is equal to 3, I guess, because I think the index still starts at 0, right? So that would be your fourth index. I forget exactly. Zybooks will be a little bit more clear about it, but I forget exactly how the index works. Whether it's like if he gives you 4, if that means like the third element because it's indexed at 0. I think that's probably what it is. So, but yeah, you don't have like it's not like you can say like, oh, your linked list at 0, right? That's just not something you guys are going to get. Removal, so you can remove the head, remove the beginning element, or remove tail, remove the element at the end. Remove pieces of like data. So this is basically you're going to iterate over your entire list, and any time that that data matches what that data is in the node, you're just going to remove that node. On the note of removal, it's not like your ABS and ABQ where you can kind of just like zero out the data or just kind of leave that node there. You actually need to like delete, like you got to call delete on that node so that it's completely out of memory. And then you have remove at, where you're going to remove a specific index, and then clear, which is just basically going to nuke your entire linked list. It's just going to destroy the whole thing. And then you have your operators. So these are the ones that can be used like with the index. So like you overload this operator so that main like the client of your linked list can actually iterate over your linked list using the bracket operators. So they can get that functionality, and that's what I talked about. Like you can build that for the linked list, but like you won't be able to use it inside your own application. Or you might be able to find a way to use those operators in your own, but like it's mainly for your client to use, right? And then it looks like you just have the equals operator. So this is just going to tell you if your linked lists are like equal to each other. So if it's got the same amount of elements and each of those nodes have the same pieces of data in them. And then you have your copy assignment operator. And then you have your constructor, your copy constructor, and your destructor. And then he goes over all of these in much more detail than I did. So that's what all this is. This one's a really solid page to read. I think not everybody, there's a lot of students who skip this page because I think it might just look daunting or it doesn't look important for the project. But it's a really solid one to understand. It basically is going over how to use the type name keyword with templated types. Because basically this nested class is a little bit awkward when you're trying to return a type of that nested class from a function. You basically have to end up using kind of this long syntax for it. But he goes through iterative trial and error on trying to get this to work, and he explains in detail each one, like why it won't work. So definitely please read this. I think it's super helpful. Tips. I think the biggest one is the best one, or the first one rather is the best one, where just start small. We give this to you guys in parts for a reason. In semesters past, we've given this this project out like at one time and basically like go ahead and do it. And I think learning it that way was a little bit challenging because it felt very overwhelming. Here we give it to you in parts, so it's easy to digest and figure things out. So my personal recommendation to starting on this is to add, like do the add head, add tail, add, and then like print forward and print reverse. Work on all those simple functions first. And then move on to your like big three. And I know that sounds like a little bit weird to not finish out your constructor stuff first. But in my experience, I think working with the simple like add and prints give you a better understanding of how your linked list is actually built. Where if you try to use your copy constructor, or if you try to write your copy constructor and assignment operator destructor, you don't have a firm vision on like how the linked list is operating. And I think you're just going to write some real weird code, and then that might mess you up even more when you go to work on the things like add and remove. So that's my personal recommendation. If you feel pretty confident with this, feel free to do whatever you want. That's just my humble opinion. So. I think that's pretty much all I had for you guys on this. Hopefully this was helpful. I know he hasn't talked about it yet, so you didn't get like a real like lecture, but hopefully when he talks about it in class, you can be like, oh, like I remember Trevor talking about that. That makes a little bit more sense now. So that's kind of my goal. So yeah. So you guys have a good day. Good luck on this project. Good luck with anything else you guys got going on. Feel free to stick around and ask questions. So.